Welcome back to Module 8. Today's learning outcome is to model actual real-world systems using the three system elements that we've come up with: masses, springs, and dampers. We're also going to define generalized coordinates, and we're going to define degrees of freedom. And so here again, we're going from some actual system, developing a mathematical model, so we have to come up with this physical model of masses, springs, and dampers. Mass, we talked about earlier. We talked about linear springs, torsional springs, linear dampers, and torsional dampers. And so in modeling, we have to use a generalized coordinate. And these generalized coordinates can go from qi equals I equals 1 through however many coordinates we need to describe the system. So these generalized coordinates will completely describe a system's configuration or location, and they can't be arbitrary. When modeling, we also refer to degrees of freedom, which are given the symbol capital N. And the degrees of freedom are the minimum number of independent coordinates required to specify the configuration of a system at any point in time. So these become unconstrained generalized coordinates. So here's an example for a single degree of freedom system. Let's look at a real-world example of this by looking again from Module 1 at a bungee jumper. So with this bungee jumper, I'm expressing the mass of the person at the end of the bungee as being that mass there. Obviously, the bungee cord has some springing action, and it also takes away energy, so it has some damping action. But we're going to say that this spring and damping portion of the bungee cord has negligible mass, and we're going to lump all the mass into the person themselves. And so in this case, I have one coordinate. That coordinate is y. It describes the displacement of the spring. If we take the derivative of it, it'll give us the velocity, and that would give us the force in the damper. And if we take the second derivative, that gives us acceleration, which mass times acceleration can be related to the inertial force of the mass moving as well. And so Qi, in this case, is just Q1, and it's equal to y. And so this, therefore, is a single degree of freedom system. Let's look at another system. This time we'll look at a pendulum with a mass at the end connected by a string to a hinge A at the top. And let's look at a real-world pendulum system and then come on back and look at this further. This is a demonstration of a real-world pendulum type system. This actually has three-dimensional movement, but we're only going to limit ourselves to two-dimensional vibration back and forth. Okay, with this pendulum, I can describe the motion with two coordinates, y sub a and x sub a, with the position out in the x direction and the y direction. So then I would have two generalized coordinate, xa and ya. But is there a problem with this designation if we're looking at the number of degrees of freedom? Go ahead and stop the video and think about that for a second. And what you should see here is that there's a constraint between xa and ya. So these are not unconstrained generalized coordinates. We have a constraint by Pythagoras' theorem that xa squared plus ya squared equals L squared. So these coordinates are not independent. So they're complete. They just completely describe the position of the system, but they're not independent. So the degrees of freedom of the system is not 2. Can you think of another coordinate, unconstrained generalized coordinate that would completely describe the motion of this system? Okay, after you thought about that, here's a system that's complete and independent. This is an unconstrained generalized coordinate where we measure the motion of the pendulum with an angle theta. So there's just one Q, Q1 equals theta, and this is a single degree of freedom system. Two good examples of generalized coordinates and degrees of freedom. We said that the generalized coordinates could not be arbitrary. So what did I mean by that? Well, here's a system, a bar AB, shown in the position here. And we could describe the position of B as how far it goes out in the x direction. We know the length, so we should be able to, we could easily find YB as well. But XB should describe the position of B. However, it also describes the position of B if the bar is in this position. And so this is an arbitrary generalized coordinate. X of B does not work. And so again, not a complete but not arbitrary coordinate for this system undergoing motion would be theta. So Q1 equals theta. And that's not arbitrary. Finally, let's look at the one more system here for degrees of freedom. We're going to study in a later course multiple degrees of freedom. And so we're not just going to come up with a single unconstrained generalized coordinate for a single degree of freedom system. Here's an example. We have two masses, two dampers, two springs. And to completely describe the motion of this system, we need the displacement, velocity, and acceleration of the mass on the left and the same x2 generalized coordinate, which we can also find its velocity and its acceleration. And so this would be a 2 degree of freedom system. Q1 equals x1 and Q2 equals x2. So as a summary, in this module, we looked at actual real-world systems, gave you several examples. We defined what the generalized coordinates are and how we come up with a number of degrees of freedom for a system. And I'll see you next time.